So this is my isometric hex game that I've been working on. The first thing you'll notice is the 3D layout of hexes. Now, there's no default layout for this in Godot, so I had to go and make my own system. For the hexes, I use the coordinates QRS, and I also have a Y for the 3D component. These axes are very similar to the Cartesian coordinates, but one of the axes is angled to better follow the angle of the hexes. We do this so that each axis can pass through the midpoint of each edge of the hex. If we didn't do this, one axis would pass through the corners of the hex, and we wouldn't be able to line them up properly. A byproduct of this is that when I put them into an array, they take the shape of a rhombus. But since I have them in chunks, I can just shape the hexes however I want instead of relying on the shape of the data structure. So, with the chunks, I needed to fit them in a structure that can be quickly accessible by index, but I also needed to be able to change some contents without having to process what hasn't been changed. The first thing that I tried to use was a standard 3D array. The good thing about a standard array is its simplicity. Let's say that, as a character, we are moving over to the right, and so we need to shift everything else over to the left. The steps that we would follow is that we'd create a new array. We would take what we already have and shift it over to the left, deleting what doesn't fit in the array anymore. Then we would take the new one that we need to fill in, and we would put that in the empty spot. The problem with this approach is that it's not super scalable. With any sufficiently large amount of chunks, the amount of data that needs to get shifted over would end up becoming too much to feasibly process in real time. So if we have a 5x5x5 grid, that would be 125 chunks that we'd have to shift over every time we move over a chunk. The amount of computational demand that we would need would increase by a cube every single time we want to increase the draw distance. I tried using graphs and linked lists, and it worked fine, but I didn't like how much overhead there was, as well as how many extra things to keep track of and workarounds I needed for working with the graphs and linked lists. And so I decided to scrap the idea. I ended up settling on a 3D array that had a custom start index, and it looped to the beginning or the end depending on which way you would move it if it went out of bounds. So if we had this array, and we wanted to shift everything over to the right and then create a new one, what we would need to do before is shift over the 4 elements, delete the one at the end, and then create the new one on the other end, which would be a lot of work. Instead, we're going to delete the one on the right side as normal, and then we're going to fill in the new one that would appear at the left end in that spot. To explain, this is what we would have before we do that. This number line are our spots in memory, and this arrow is our custom start. Now to start off with, this will match our normal first spot in memory, but when we delete the one at the end and fill it in with the new spot, what we do is we take our start and we move it to the left. Now, the left would bring it out of bounds, and so we'd loop it back around to the end, which would be exactly where we want our furthest most one on the left to be. So what we have is the one that's furthest to the left is in memory actually all the way on the right. We just have an arrow pointing to it to say this is where the start is, and then when we process all of them, we count until we reach the maximum amount, which is 5. We just start at that end and loop all the way to the front until we get to the end. And as you can see, if we do that one more time, everything will still be lined up, as we'll now start on this dark blue dot and move over to the right, and then loop back over, and everything still fits. Now, I don't know if this is the best approach, but this allows me to only work with things that I need to change and not have to process anything else. One important hurdle that I had to get over was figuring out a way to find the hexes and chunks without having to loop through anything or search for anything. So each hex is in a 3D array inside of a chunk class, and each chunk is in a 3D array inside of a chunk manager. Let's say that we want to interact with hex 135. To do that, we're going to need to figure out which chunk that hex lies in. To get the chunk, we're going to need to know how many hexes there are in one direction in a chunk, so the length of the chunk. Then we need to take our hex number and divide it by the length of the chunk. That'll give us an approximation, which we can then discard everything after the decimal. This number is our chunk number. This means that hex 135 lies inside of chunk 16. And so now we have our hex number and our chunk number. The only problem is that we still don't know where they are in memory. Okay, let's set up the scene a little bit. Let's say that we have our grid, our chunk array, and let's say that we have 16 as our center point. But let's say that we moved around a little bit, and so the memory behind the scenes is a little bit different. To get what we're looking for, we're going to need to get the lowest chunk number, not the one that's in memory, because if we get the one in memory, we would get 16, but that's our center point. Really, we want 14. So how do we get it? Well, we always have a reference to our current center chunk. So what we need to do is we need to take our current center chunk and subtract it by our radius. This would give us 14, which is our lowest chunk. Using this, we'll be able to find any chunk in memory. Now, based off of looking for hex 135, we need to get chunk 16. To do that, we take whatever chunk we're looking for, which in this case is 16, and we subtract it by our lowest chunk, which is 14 in this case. This will give us 2. Now, if you're paying attention, you'll see that 2 would actually be our spot in memory if we were starting from chunk 14. And so we need to calculate the offset in the data structure for the chunks that we're using with that moving starting point. One of the tools that we'll be needing for this is our chunk diameter. Usually it would just be 2 times the radius. However, in this case, we need to add an extra 1 to always account for the center chunk, which will always be an odd number. So with that, we're going to take our starting index, which is 3, and add it to the index we're looking for, which is 2. Then we're going to use the modulo operator, and we're going to use that by the chunk diameter that we just found earlier. In this case, that would be 5 modulo 5, which would give us 0, which is the index that we're looking for. And this will work with any chunk that we're looking for. If we wanted chunk 17, our index would be 17 minus 14, which would be 3. Then we'd take 3 plus our starting index, 3, which would give us 6. And then we'd do 6 modulo 5, that would give us 1. That would be our next index. So we need to get chunk 16, which we now know is an index 0. So we take that, and now we need to get the hex that we're looking for. So the hex that we're looking for is 135. And we'd use the modulo operator by the amount of hexes per chunk in one direction, the length of the chunk, and that would give us the hex that we're looking for. Since these are always in order, we don't need to do any offset, so we're done. And with that, we have working chunks. For pathfinding, I implemented A*. It works fairly well. However, since we are restricted to the floor, we fall into a lot of A* traps. So if we're at the base of a mountain, and we want to get to the top of that mountain, but it's only 1 hex to our right, we'll end up having to check in a radial pattern around until we find a spot to actually climb that mountain. So instead of checking however many, like dozens of hexes, we'll end up having to check hundreds until we find that base, where our heuristic will finally work again. I have a few ideas for how I could get around this, or at least make it a little bit better, but I've yet to actually try any of them, and I'm unsure if they would actually be more efficient. Some of the ideas I've had would be to create a direct line, so turning off the need to be able to stand on the hex, and then maybe using that line as a heuristic. The only problem is that a lot of times the ideas that stem from that will make the worst case scenarios worse than they already are. Even if the best case scenarios are a little better, it's usually not worth it. The other ideas I've had are just kind of brute forcing it, so multi-threading, which could just make the search faster. Another thing is maybe starting at both ends, and then whichever one gets there first is the one we take. Another idea I've had that actually was good was starting at both ends, and then whenever either path touches the currently searched hexes of the other path, we would just connect the paths that are currently there. The only problem is that while it is faster, sometimes the pathing would be a little bit weird. Regardless, even if it falls into a few traps, it is fairly reliable and will usually give me what I need, so I've opted to move on and focus on more pressing things. The next thing that I needed to figure out was the players, the enemies, or objects, or anything that isn't one of the hexes, really. One of the options would be to store them where we would put the hexes, or in the hexes. The only problem with that is we'd have a lot of memory in use that is actually just empty, just as a placeholder for if we need it, and I didn't like the idea of that, so I looked for other options. The smallest amount of memory use would be to keep track of the hexes that are occupied inside of the entities. So if an entity takes up a few hexes, they keep track of that. The problem with that is if we need to find something by the hex, we would have to search through all of the entities until we get that hex, which would be super slow. I opted for a bit of a mix. For the entities, they each have an array which keeps track of which empty hex spots they take up. And for the other way around, I have a dictionary that has the hex coordinate space as a key, and the value is a linked list of entities. This just allows anyone to have multiple entities on the same hex if necessary. Then the character keeps track of where they are, and if they move to a new hex, we update which hexes that they have in their own space, as well as that dictionary. When we have characters that are bigger and take up multiple hexes, it can be a little bit difficult to figure out which hexes they should occupy. The idea I had to get around this would be if a character takes up an even amount of hexes, instead of using the center of a hex, we'll actually use the corner of one, and each hex that touches that is what they occupy. Getting the corner is pretty simple. We just need to figure out which hex the center is on. Then we need to figure out what angle that is in relation to the center of the hex, and then we take it in increments of 60 degrees, and whichever one is closest is the corner. And then, of course, I have a simple state machine. This is for determining what the game state is, so in exploration mode or in combat, or whether on the title screen or things like that. And then if we're in combat, it is also what I use to determine what the selection screens are, what the character's abilities and actions and other such attacks and whatnot are. The actual actions aren't very sophisticated yet. I've come to the realization that I need to have a bigger and better plan for what the actions will actually be doing before I go and implement a bunch. There are a few more things that I've done that are very early and very experimental, and so I don't plan on actually showcasing those things today, which would bring us to the end. And so, thank you for listening to me ramble for the last 10-15 minutes. Bye-bye now.